Hi, we are from Group 1 Multimedia Computing TMF 2234 Operating System, and we want to present about performance analysis of round-robin CPU scheduling with context switching overhead. My name is Nu Atira binti Sabli. My number metric is 105552, and my teammate is Joanna Mary Anna Abel 104558. Muhammad Azhar Rais bin Abdullah 104998, and Ahmad Zulfahmi bin Zulnazar 103128. In multitasking operating system, the CPU scheduler is responsible for sharing the processor among multiple processes. One commonly used scheduling algorithm is round robin, which is popular in time sharing system because it is fair and allow each process to get CPU time. However, the performance of round robin depends heavily on the time quantum. A very small quantum causes frequent context switching and high overhead, while a very large quantum reduces system responsive. In this project, we simulate, we simulate the round-robin scheduler using 100 process with three different quantum values: 3 millisecond, 10 millisecond, and 25 millisecond. A fixed context switch penalty of 1.0 millisecond is applied. We evaluate the system using average waiting time, average turnaround time, and total CPU overhead to determine the optimal quantum size. Next, I will briefly explain the process representation used in our simulation. Each process is represented using a process control block or PCB. The PCB stores important information needed to manage execution and calculate performance metric. Each PCB includes the process ID, arrival times, burst time, remaining execution time, finish time, turnaround time, and waiting time. Arrival times are randomly generated between 0 and 100 milliseconds, while burst time range from 5 to 50 milliseconds. This structure allows the scheduler to accurately track each process throughout the simulation and ensure precise calculation of performance metric, following standard operating system models. Now, let's look at the key constraint in our simulation, which is the context switch penalty. In our implementation, a fixed 1.0 millisecond overhead is at every time a context switch occurs. This happens in two cases: when a process completes execution and when a process is preempted after its time quantum expires. To model this, we update the global system time using the formula shown on the slide. Current time equal current time plus execution time plus 1.0 millisecond. This approach allows the simulation to accurately capture the CPU time loss due to context switching and form the basis of our performance analysis.
Now, let's look at the engine that drives our simulation, the time logic. The simulation utters a current time global variable to calculate the total duration of CPU activity and system overheads continuously. Next, have idle period synchronization. Idle period synchronization is to handle idle CPU states. The timeline automatically advances current time to the specific arrival time of the next pending process whenever the ready queue is empty. So for the actually process, we use primitive execution logic. We definitely calculate as the minimum of the remaining burst time of the accurate time quantum, accurately reflecting round robin progression. Finally, and most important for realism is the context switch overhead. Switching is not free. We add fixed 1.0 uh, millisecond penalty is added to global timeline after every execution segment. Related to the quantum expression of process termination to select relative performance costs. So it's allowed to select relative performance costs.
Code architecture and methodology. Language. Developed in C++ using an object-oriented approach. Clay classes struct. Struct process the PCB class round robin scheduler, the engine that manages the ready queue and the timeline. Struct simulation result stores the final data for comparison. Robustness built to handle 100 processes across the three different runs. Q equals 3, 10, 25 within one execution. Randomization and data generation. Version Twitter MT19937 explain that you use the C++ random library rather than RAND for higher quality statistical randomness. Uniform distribution ensure AT and BT are distributed evenly across the required ranges between 0 to 100 milliseconds and 5 to 50 milliseconds. Pre-sorting. Processes are sorted by arrival time before the simulation starts to ensure the queue populates correctly.
To ensure the reliability of our simulation, we implemented multi-layer verification. First, we included a visual verification feature where the code prints a live progress update and a final comparison table directly to the console. Second, the system ensured data persistence by automatically generating two detailed CSV files. The first file is a process detail file. This contains raw data for all 100 processes, including arrival times, burst times, finish times, waiting times, and turnaround times, all measured accurately in milliseconds. While the second file is simulation result file. This provides a high-level summary of the AWT, AT-AT, and total overhead for the three tested quantum values.
Moving at the average turnout time or ATAT. Basically, this metric tells us the average lifespan of a process, measuring the total elapsed from the moment it arrives in the queue until it completely finished execution. So right now we can look at our mission results. The trend is immediate end of use with a small quantum of 3 milliseconds. Our average turnout times which was huge over 2600 milliseconds. But as we increase the quantum to 25 milliseconds, the time drops significantly to roughly 1770 milliseconds. So the larger quantum actually allowed process to finish much faster on average. Why did this happen? It becomes down to cumulative overhead impact because the 3 milliseconds quantum forced the CPU to switch context constantly. We are paying that 1.0 millisecond penalty hundreds of the time of the times. This creates a computation delay. A secondary of switching just not the CPU, it aggregates over the time, extending the total completion time for the entire batch of processing significantly compared to the 25 millisecond run. In short, while a small quantum feels fair because everyone gets a turn quickly, the cost of switching actually makes everyone wait longer to finish.
Average waiting time measures how long a process waits in the ready queue before completing execution. From the results, the smallest quantum of 3 milliseconds produces the highest waiting time because the CPU is frequently interrupt by context switching. As the quantum increase, waiting time decrease since processes are allowed to run longer without interruption. Therefore, a larger quantum helps reduce waiting time by minimizing unnecessary preemption.
Next, we move to our efficiency analysis. Total CPU overhead represents the time the processor spends purely on task management rather than executing process instruction. We calculate this metric by multiplying the total number of contexts switched by our fixed 1 millisecond penalty. The data reveals a severe performance penalty when using smaller quanta in this environment. At the smallest quantum of 3 milliseconds, the system performed 962 context switches, wasting nearly a full second, specifically 962 milliseconds, just on overhead. However, as we increase the quantum size, efficiency improved dramatically. At the medium quantum of 10 milliseconds, overhead dropped to 323 milliseconds, and at the largest quantum of 25 milliseconds, it fell to just 154 milliseconds. This represents an 84% reduction in wasted CPU cycle compared to the smaller quantum, proving that a larger time slice is essential for maintaining system throughput when context switching costs are high. To wrap up our study, we looked at the trade-off between latency and efficiency to reach a definitive conclusion. We have identified the large quantum, which is 25 milliseconds, as the optimal configuration for this specific processor constraint. Our reasoning is based on the significant impact of the 1 millisecond context switch cost. While a 3 millisecond quantum might theoretically improve responsiveness in other systems, here it proved highly inefficient, consuming 962 milliseconds in overhead. The 25 millisecond quantum strikes the best balance. It minimizes that expensive overhead to just 154 milliseconds, while effectively lowering both the average waiting time and average turnaround time. Therefore, we recommended that for any environment with high context switching penalties, the best strategy is to maximize the quantum size to reduce frequent switching and optimize overall performance. That's all from us. Thank you very much for your time and attention. Have a great day.